Alright, so today we're going to do a problem on the inverse function theorem. So consider the mapping f from r squared to r squared defined by this, and then find the derivative of the inverse function at the image of the point uv equals 1, 1. So what does the inverse function tell us? Well, it just basically tells us when a function can be locally inverted, and this is really important. So it doesn't tell us if it's globally invertible, it just says there exists a small neighborhood where it is invertible, aka it's 1-to-1 and onto. So the hypotheses, well, let's just first see if this satisfies the hypotheses. So like the domain is open and P is in the domain, that's true. So you can see r squared is open. Also 1, 1 is obviously an r squared. Next, it's continuously differentiable. So this means that all the partials exist and are continuous. Well, in order to check this, we're going to have to take the Jacobian of f uv. So let's do that. So f prime uv is equal to, and then this is going to be d1 f1, d2 f2, f1, d1 f2, and d2 f2. And that's going to be, so this is f1, right? So that's going to be 2u negative 2v. This is f2, so that's going to be 2v, 2u. Now, how do we see if this is continuously differentiable? Well, let's look at each of these. Yep, they're, polynomials. These are all continuous and differentiable. They exist and they're continuous. So yes, that is true and that is true. And now let's check that determinant at the point is not 0. So to take this determinant, just do AD minus BC. So det 2v, 2v, 2u. It's going to be equal to 4u squared plus 4v squared. So that's going to be equal to 8 at 1, 1. So that's not 0. And we're good. All right, and notice that this cannot be inverted at 0 at the origin because the determinant is not 0. Of 0, 0 will not be 0. All right, so now we know that there exists a small, or maybe not small, but basically just exists a neighborhood containing P, so containing 1, 1, and a neighborhood containing f of P. So what f maps this to, and so the image of this, such that f of u equals v, aka f is 1-to-1 and onto here in this neighborhood. And the inverse will also be C1, so it's also continuously differentiable. And in these open sets, df inverse is equal to the inverted matrix of dfx. So this is the key thing. Let's calculate this. Actually, I don't need this. I just don't need this. Okay, so again, this is going to be dfx. So maybe I should do this. Okay, so this is dfx. And let's invert this. So when we invert this, what do we get? So remember that when we invert a 2x2 matrix, it's 1 over the determinant, so 1 over 4u squared plus 4v squared times the matrix where the main diagonal, or reverse the main diagonal and negate the off diagonal. So this is going to be 2u, 2u, and then negative 2v, 2v. Because we're reversing these, it's the same, and then negating those. And then finally, we just have to plug in our point 1, 1. We know it's invertible here because, again, the determinant was not equal to 0. So at 1, 1, this would be equal to 1 over 4 plus 4, 2, 2, negative 2, 2. That's just equal to 1 over 8 times 2 all across. So 1 over 4, 1 over 4, negative 1 over 4, 1 over 4. And that is going to give us the derivative of the inverse function at the image of the point uv equals 1, 1. And we're done.